In the last video, I've talked about these typical magnetic flux density that are around us, from the human brain, the Earth's field, refrigerator magnets, or MRI. Now, in this video, I want to talk about maybe some typical magnetic field that we can easily produce ourselves in our own home. Nothing dangerous here. I'm just talking about maybe using, say, a cheap battery that you can buy from the shops of 1.5 volts, just a typical battery that I'm going to connect to. Say I'm going to connect this to a long piece of wire. Okay, I'm going to connect this to a straight piece of copper wire. Well, those are copper wires, of course, as well. So I'm just going to focus on this piece of wire for now, this straight piece of wire, and let's say this is quite long, right? This is quite long, maybe 30 centimeters, half a meter, fairly long by human standards. So, right, let's think about what kind of current can go through here. Now, typically a battery would have some internal resistance of about 3 ohms or so if you buy this battery from a shop. So if I'm just going to connect a piece of wire directly to it, I would expect a current of, let's see, we're talking about Ohm's law here. So V equals to I R, and R is equal to V over I. So V over I, 1.5 divided by 3 is about 0.5 amperes. So we're talking about a current of about 0.5 amperes that go through this. Okay. Now, just to make things easier, for what I want to do afterwards, I'm just going to say that there is a current of about 0.1 ampere going through this. Okay, maybe I will. I'm just going to add maybe some resistor here, so as to get a sort of a round value for the current. Let's say I add a resistor here of about maybe 12 ohms. All right, if this is 12 ohms, when you use Ohm's law, this will work out to 0.1 ampere. So there is this current going through here. Okay. Now, as it turns out, when there's a current, the electric current would actually generate a magnetic field around it. Now, it's the magnetic field around a straight wire is perhaps less familiar than the electric field in a coiled wire. So let me quickly draw that too, so that we have something more familiar to look at the same time. Suppose I have a battery, my usual, my same 1.5 volt battery. So 1.5 volt battery with typical resistance of 3 ohms, and I'm just going to connect it to, like before, a 12 ohm resistor. Okay, so as to give a current of 0.1 ampere. And down here, I'm going to, instead of a straight wire, I'm going to connect this to a solenoid, to a coil, alright, of a number of turns. Now this should be more familiar because this coil is what we could put, let's say, a piece of iron inside. And if I put a piece of iron rod inside this coil, I will get an electromagnet. Okay, so this setup is something that we know would produce a magnetic field. So if I have a straight wire, right? If I have a straight wire, it's reasonable to expect that this would also have a magnetic field. Maybe the pattern of the field will look different. So I'm going to describe that later on. But for now, what I'd like to do is to talk about the kind of typical strength, the kind of magnetic flux density we might expect from such a simple setup that we can actually make ourselves. Okay. Now the strength of the magnetic flux density of, say, coming out from this wire would be stronger, would be bigger when we are closer to the wire, would be weaker when we are further away. Okay. Now the kind of pattern, the kind of pattern of the magnetic flux density that we would actually see around here, it would look something like this. Let me try and draw it. Okay, maybe I'll draw this one first. This one is more familiar. So this would actually look just like what we know of a magnet. Now, inside here will be straight lines, magnetic fields that are straight lines. Okay, and outside here, some of these would just go straight, some would start to curve, and some would curve around. Likewise for here. Okay, so depending on which way we coil this around, one side might be North Pole and one side might be South Pole. So let's say this end is North Pole and the magnetic field would have directions. Okay, so that looks pretty much like the magnetic field from an ordinary piece of magnetic rod. In the case of a long straight wire, however, the field will have a different shape. Right? Clearly, this is straight and that's coiled, so it must be different. And it would actually look like this. It would look like circles that go around this wire. And that's the direction. You might imagine lots of circles going around. Okay, and it's not just in the middle, it's all through the wire. So I would have magnetic field around each and every point of the wire. Alright, just everywhere. Everywhere there is current, there is magnetic field around it, and this would be the directions of the magnetic field. Okay. Now I've tried to draw it to show that to show field lines that are closer together near the wire and further apart when you're away from the wire, and that's kind of reasonable to expect that if you go further away from the current, the magnetic field should become weaker, and when you're very close to the current, the magnetic field would be stronger. And if you look at the directions that as I've drawn it, look at that, take note of the arrows. There is a way to determine the direction of this circulation, the direction of the magnetic field around the wire. It is called a right hand thumb rule. Let me write this down. Okay. A right hand thumb rule. Now what this means is that you take out your right hand, point your thumb along the direction of the, place your hand close to the wire, or imagine that, point the thumb of your left hand in this direction, in the direction of the current, and then wrap your four fingers around this wire. Now if you do that, your fingers, not the thumb, but your four fingers would point in the direction of this magnetic field, and that's the right hand thumb rule. Okay, so that's a description of the magnetic field. And so what would be the strength of this magnetic field around here? How many Tesla, for example, if I have this 0.1 ampere of a current? Now, there is an equation that allows us to calculate this value. Right. Suppose that we talk about, say, a certain distance. All right, a certain distance, maybe from here to here. At this distance, let's say that's 10 centimeters, 0.1 meters away from the wire. So what would be the strength of, is there a way to find the magnetic flux density at this distance? To find the B. Okay, so if let's say I call this distance R, and that's the B there, and I have a current. The current is I. Now this is a fairly simple setup, so we would expect that the magnetic flux density should depend on the distance from the wire. That the further you are from the wire, the weaker, the smaller the flux density should be. And in a similar way, we should expect that the magnetic flux density would depend on the current. So the bigger the current, the stronger should be the field. And indeed, there is a formula. Now, if you are watching this video to study for your A-level physics, you would most likely not be required to know this formula for your exams, but you could just look at this as, say, an example, right? An example of doing a physics calculation, just to get an idea. Now, or if you're interested in knowing this for general knowledge, there should be a B, by the way. Right, that's also an interesting thing to know. Okay, so this is actually the formula that would allow you to calculate the magnetic flux density if you're at some distance from a long straight wire with a current going through it. There's a mu naught here. Now, if you remember the Coulomb's law for electric field, there was also another funny symbol there that looked like an E, which was the Greek letter epsilon. And that was called the permittivity. Now, in this case, I have this Greek letter here, this is also a Greek letter and is pronounced as mu. So it's mu with a little 0 at the bottom. Now this mu naught has a name. It is called the permeability. And the value, it's a very small value like the permittivity, it is equal to 4 pi times 10 to the power minus 7. Now I shall not try to write down the SI the units for this. I'm just going to put bracket SI to say that this number is in SI units. Okay, so I shan't go into the details of the units for now. The formula, this formula would then allow us to calculate the magnetic flux density, say at 10 cm away from a current of 0.1 ampere. So let's try that out. If I use this, if I put in these numbers, if I put in 0.1 ampere into there, if I put in 10 centimeters into there, which is 0.1 meter, and if I put in this number into the magnetic into the permeability, okay, then I would get an answer which is roughly, I shall not calculate an exact value for this, but just for this example, we would find that roughly the magnetic flux density in this case is 10 to the power minus 6 over Tesla. So just a very weak field, right? Long straight wire, very weak field. Now just in case you wonder, you might wonder what happens if this wire is very short. If this wire is very short, then surely it doesn't look like a long wire anymore. So indeed, if that is the case, if the wire is very short, then this equation will not be accurate. This equation is only accurate if the wire is very long compared to the distance r. Okay, so and in fact, this field pattern, this magnetic field pattern, is also would also only look like this if you're close to the wire and if the wire is the long wire is really long compared to the distances around where you draw this pattern. So this is the typical field that we might expect. And if you remember the last video when I talked about the Earth's magnetic field, now 10 to the minus 6 is a micro Tesla. You might remember from the earlier video, the last video, that the Earth's magnetic field is about 30 micro Tesla. Right, the Earth's magnetic field is about 30 micro Tesla. So 1 micro Tesla, 30 micro Tesla, okay, is a lot smaller than 30 micro Tesla. But if we go closer to the wire, to maybe instead of 10 centimeters, maybe to 1 centimeter, the strength would increase. Right? You see that R is at the denominator, so it just means that if R is decreased by 10 times from 10 to 1 cm, okay, this is decreased from 10 to 1 cm, we would expect this magnetic field to increase to maybe 10 Tesla, 10 micro Tesla. So that starts to be close to the Earth's magnetic field. And indeed, the wire, this current, this 0.1 ampere current, which you can easily produce using a battery that you can buy from the shops, this would actually have a visible and obvious effect on a compass. If you imagine taking a compass needle, let's say I have a compass here, compass needle, that's the north. Try and draw a compass. So let's say that's a compass in a case. Okay, and that's the north, that's the south, the needle. Now if I take this compass and put it quite close, maybe 1 cm or so away from the wire, the compass needle would actually rotate under the influence of this field. Okay, because this field could be comparable. All right, comparable means either nearly as strong as the Earth's field, or maybe just a few times different. Okay, if we are talking about such fields, then this would have a visible effect on the compass. Visible as in when you bring the compass close to this wire, you can actually see the compass needle rotate very obviously. And in fact, that a few hundred years ago, right, that was how a scientist discovered that a current can have a magnetic field, just because it so happens to have this wire connected to a battery and put it on top of a compass, and he saw the compass needle rotate. Right? That's how it was discovered that there is actually a magnetic field around a current.